So over the weekend, I started working on the serialization framework, something like a very lightweight serialization framework for C++. And I wanted to make it generic. And a lot of the frameworks I've seen in the past, right, required you, like before you could serialize a type, so you had a struct, like whatever, struct with some fields. That struct had to usually like implement an interface and have like a serialize, unserialized method, or it had to have some method at least, or play somehow with something else. And is there a better way to do this, right? Could you start serializing types, like say, how are you gonna subclass std string or vector or map, right? And if you still want to be able to serialize those, so I can tell you that protocol buffers can do it, but I think they do it slightly differently than what I came up with. So before we get into protocol buffers, let me show you, just show you real briefly what I was working on. Let's start from the top here. You can ignore the struct n for now. I just like to create these noisy types where I just print what's going on with it, right? If it's being copied, created, copied, copy constructed, move constructed, assigned, and whatever. And then let's look from lines from between 26 down to 35. And we can start going through it with a debugger too. Let me just switch to this project. So so at first, let's just say we want to just serialize and unserialize, unsigned int 8-bit, 16, 32, and 64-bit, right? Like you see here in line 34. And all this does, I'm just feeding it some variables with some values, and I say, hey, pack it, right, or serialize it. And output here is a buff1, which is the buffer one. In this case, I'm using a vector of std byte. And then later on, right, I want to just unpack it. And given the buffer, right, I need to know, because I'm doing this like statically, I need to know what types there are. So I just feed them here on line 35 to the unpack, and it's going to go through this buffer and pull out all these types out of the serialized data, right? But what I wanted to do, for example, is add something called a pack and unpack transforms, right? So what line 26 means really is that, hey, framework, whenever you come across a unsigned int 16t, when you're being told to pack it or unpack it, run this little transform on it. Okay, it's a simple lambda. And what this lambda has is just two parameters. First is going to be the value of that actual uint 16. And I shouldn't be jumping to it. And the second is just a buffer output type, it in this case. And buffer output type is defined as back insert op iterator, I think. That's what I defined it as. There. Yeah, it's just a back insert iterator into a buffer. So, right, a nice thing about operators is that they kind of work like pointers. I mean, not operators, iterators. Right? So here, and I created some support functions. And notice what happens here. I'm telling it when the framework comes across this type, it's going to, instead of doing a default serialization, which the default case is just bit by bit copy into the buffer, I wanted to say, no, hold on. When you find int 16, I want you to pack this value, but before I give it to you, I'm going to run it through H2NS. And some of you may know what it is. It means host to network short, right? So this changes a integer value representation from whatever is native on the host, which could be big endian or little endian, and it switches it to network short, because it's a short, because it's a 16-bit, and a network byte order. And network byte order is big endian. And then do the same thing for 32 and 64, right? And then on the unpacking side, now I add a unpack transform. I say, okay, now when you're unpacking from this buffer, whether you see you in 16, 32, or 64, here's the signature. Here's what I want you to call this little transform. And the signature of the transform is, in this case, buffer input. That's just another iterator that you can read from. And a pointer to storage. And this is important. This storage is already allocated. So I will call you, and I will give you a pointer to a memory location. And I could change this to void star. it would work just as good. I wouldn't have to change anything else in this signature. I wouldn't have to change it here or anything, just signature of this lambda. But anyway, I prefer stronger types, so I keep it that way. And what this means is, hey, when you come across this type in a buffer, here's the buffer input. So here's the source of where you can read this type from, and here's what I want you to store it. And you go figure out how you're going to do it, right? So I'm giving the user everything they need, which is where to read from and where to write. And how you want to process that piece of data, it's up to you. So in this case, I'm saying, okay, unpack value, which again, unpack value is just bit by bit copying out of the buffer. And I'm telling you, hey, okay, go unpack from this iterator location, unpack 16 uint 16, and then pass it back to, in this case, N2HS. So this is the opposite transform. This is the network to host short. So this takes it from the big endian notation, which is the network byte order, to host. Now, what's nice about this? I don't need any of this if I just want to serialize and unserialize data on the same machine, right? Just store it to this and read it off, or even send it over the network to another machine of the same architecture. But here, because I introduced these three packs and unpacks, I can now say serialize it on, I don't know, a little endian machine like an Intel, and send it to a big endian machine. Like, I can think of one off the top of my head, but I think Motorola's Power PCs were big endian. I'm not sure about Alpha. I used to have an Alpha 64-bit PC years ago. It's actually my first 1 gigahertz CPU. But anyway, so right, this is a very common thing to do when you're serializing and unserializing numbers. So let's see if we can run through it. And let's see what's gonna happen. And this will eventually lead us to protocol buffers, I promise. But is this at all interesting to you guys today? I hope so.
Definitely.
All right, sweet. Yeah, because I've actually been working on it like insanely since last week. Since really after Scott asked this question during the class on Wednesday, I kept thinking about it. And I always wanted to write something like this in the past. I always wanted to create like this type of generic serialization and unserialization framework that's lightweight, that doesn't require you to, to have your types be integrated with the framework in any way. Okay, so here we go. We're adding a pack transforms. We're adding 1, 2, 3, and let's say I'll put a breakpoint in one of them. I don't know if it's going to actually put a breakpoint. I'm going to put a breakpoint. Enable breakpoint in below. No. I mean, we can step into it. And then unpack transformed, and then here. So now we're going to jump into the pack function, and this is a type of C++ code that, if I read code like this, say 3 years ago or 5 years ago, I would have cried because I would have had no idea what is going on. But okay, so here we go into pack, right? Template parameter pack thingy. So let's just allocate a buffer, and you will see once we go through this, like this whole thing that I did so far, this whole framework, 275 lines of code. That's all there is to it, and it's already incredibly powerful, and can be extended to basically handle any type you want, without either A, having to modify the framework at this point, or B, having to modify the type. So here's, I'll get into this buffer size thing later. This is an optimization I've introduced, where given a set of values, each one of them is pushed through this pack size thing that then looks for a pack size proc, and I'll explain what all this does. But it basically, it's going to tell me how much memory this sequence of things will occupy, so I can pre-allocate it in the buffer, so I can do this reserve. It's purely optimization, it's not required, but I figured it's nice to have. So if you look here, what am I serializing? Uint 8, 16, 32, 64. So that's 8 plus 4, that's 12, plus 2, 14, 15 bytes in total, right? I'm serializing. So let's see what the buffer size is going to be. Oh, look at that. It's 15, right? So it computed it. It hasn't serialized anything yet, but it computed it. So then I reserve this space. And let's prove that it actually was 15. Now, if I go just step right over this pack type thing, that's going to pack all the types. Bam! Look at the buffer. The buffer size is 15, and I told it was going to be 15. So that's nice because all these pushbacks and all these copies into the buffer inserts and whatever it is that I'm using is now basically free, right? It doesn't have to do any reallocations and moves. Okay, so let's go through this again. Bang, 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 transforms, step into pack. Let's see what happens now when I go into pack type here. There we go, pack type. And here I had to introduce some overloads because, well, because I didn't it turns out I didn't know the type system as well as I thought I did. So I had to, there was no way for me to go around this without these two pack type overloads, one for universal reference, one for pointers. You see all the pointers are important. So next thing that happens here, it says, hey, get pack transform. So what does this mean? It says, hey, is there, for type T, has there been a type transform register to somehow process this type differently? So let's see, let's go into here. And the first thing I do is I define a static default pack transform in case I don't find one, right? And the default one just takes a constant void pointer to something, takes an output, and it will just pack this value. And since I have the types here, I can now capture this type as a cast inside the simple lambda. I had to do a type decay. Let's not get into that. But let's just say I had to. So that's the default one. But then we'll go look through these maps. And how we're going to look through these maps. We're going to take a hash code of type ID of this type that we're looking for. And that's how the framework does this registration. So it takes a type ID of this type, gets a hash code for it, and in the map inserts a mapping between the hash code of this type and a generic lambda, like this pack transform lambda. But when you're adding it, say, see if you do like the add pack transform, it takes this generic, no, not this generic lambda, it takes this lambda with these specific arguments, right? Like already has this specific type, but that's not what it can hold in a map, right? I could not store a lambda in a map that one of them takes int 16 and the other one takes int 32 because these are two distinct types. But what I can store a generic lambda that just takes a void and a buffer output, but it captures by value the lambda that I passed in, and it also happens to capture this typecast. So that's a neat. That's like it's basically I'm doing runtime polymorphism without doing runtime polymorphism, and it's still the type information is erased in a sense when being inserted into this map, but yet it still exists because it's wrapped inside this generic lambda. So okay, let's see if we find something. No, we didn't find it. Why didn't we find it? Because we're doing unsigned char, right? And I didn't register anything for unsigned char. This is just a 1-byte type. So I get the transform for it. It does the default transform. Nothing happens there really. If I step again, now this is doing for unsigned short. I step in here, this time, there, return. That second. So it found the transform here. All right, so let's step out of yaw. And here we are. And now we have serialized these 5 values of different sizes into buffer 1. Buffer 1, you look at it, you'll see it has all these 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 7, 8. That's the third value, fourth, and then finally the 64-bit value from here to here. Now if I go through the unpack, click, it's going to give me a tuple 1, 1, 2, 3, 4, right? I serialized 1, 2, 3, 4 values of these 4 types. Here are your types. Here are the values back out. So everything matches. Simple, nice. I also wanted to introduce certain other type of optimizations. So for example, when packing, see here I said, okay, pack in UN64 as UN64, or pack it as whatever you want. but the size here is the same. And so for every pack transform, right, you have to add a corresponding unpack transform, and they have to be aware of those types and type sizes. So if you mess up here, and you in a pack transform you push 64 bits into the buffer, but then you pull out 32, that's going to be bad. This framework doesn't do any checking as it goes. I initially had it do like type tagging, but it was just becoming stupidly complicated, where type hash code would be mapped to a unique, integer number, and then it was getting kind of messy because I couldn't really generate those integers on the fly, because then they would have different values depending on the order in which they were generated, and so I had to have a function, something called add type tag or something, where for each type that I want to work with, I had to at least tell the framework. So I decided to get rid of it completely, and I did so because that information can just be part of this packet. So if one requires a schema and more type information, well, you can just pack it right here along everything else you're doing. And the different type of transform I wanted to do was say, okay, if you see a size t, pack it by casting it to a 1-byte value. So there's definitely going to be a loss of data there. But why was this important to me? Because size t, if you compile, you'll see it's a 32-bit code, and size t is 32 bits. On a 64-bit machine, so if you compile something corresponding to it on the server side, it's going to be a 64-bit code, and suddenly size t is going to be 64-bit. So that can again get you into trouble with serializer and unserializer, because it's like you're pushing int on one side and you're expecting an int to come out on the other side, but it actually long comes out, and then your data stream gets corrupted. So I wanted to be able to say, okay, fine. When you're packing size t, store it as uint8. And then again, when unpacking size t, I'm going to give you the storage for the whole size t, but just unpack an 8-bit value from the stream, and I'm just going to cast it into this location. But there was one other thing I needed, right? I showed you this buffer size computation optimization earlier inside pack, where it tells you how many bytes to pre-allocate. So I needed a way to do this too. So another thing you add to the framework is add pack size proc. And all it does is for any given type, instead of just doing size of that type, which is the default behavior, you look here somewhere, the default behavior for type packing and computing the size is, let's see, what was this code? Unpack transform now, pack size proc map. There you go, the default, get pack size proc. So the default way to compute the size of a type is just to return size of t, right? You're going to get a pointer to this type, still to this value, but by default, it's going to be ignored. Just return size of t. So for size t, when serializing it, I just said, okay, I'm going to pack it and unpack it as uint8, so just return a uint8. And you'll see why this pack size proc becomes important for different types. So let's break here now, and let's go. So here we are. We're packing size t, step over it, buffer 2-1. It's only 1 byte in size, right? I pushed -1, which was a pretty big value. Get 0xFF, because it's just taking the lowest 8 bits of it. And then again, unpacking it. So I'm telling it now, okay, now unpack. And if I go, well, I don't need to actually go in here to pre-allocate anything. But in the packing, you would see, let's rerun it. Let's step into the pack function. This buffer size here being computed is going to come out as 1, because it's going to involve that custom, there you go, buffer size. It tells us 1, even though we're packing unsigned long, which is basically a size t. There we packed it into 1 byte. Unpacking, well, again, unpack it back into a tuple with the right value. Of course, there was data loss, right? It was -1 on the unsigned. It's just all bits set. So something you got to be aware of if doing something like this. But this could easily be in this add pack transform. You could check this value that's coming in, and I don't know, throw an exception, right? And say, hey, nope, can't pack it because you're asking me to shrink something from 64-bit to 8, and I'm quite certain you're going to lose some data. Now I can remove these transforms after using them and then retry this process again. So now I'm going to pack a size T again into buffer22. And this time, buffer22 is 8 bytes, right? It has all the bits. And then unpacking it, 2.22, bam, we get everything that we put in. So that's another type of optimization. And let me show you how you can add more custom types, right? So let's say you wanna pack a string like this, right? Well, by default, it would do a bit-by-bit copy, right? But this is a pointer. So you just copy a const char star pointer. That's not what you want. So you can add another pack transform and say, hey, so when you get a const char star to pack, get its actual length, right? Use str_len string length. You see how long it is. Then pack its length followed by pack its bytes. So these are like support functions, the pack type and pack bytes, and there's also pack value that I created. The difference here is that if I kept these size T transforms from size T to uint8, and then I called pack type, it would then try to apply these transforms before packing this string length. If I just did pack value, it would skip them. So in this way, by using pack type, the framework kind of calls itself recursively. So even though here you're packing another type, or here I could be packing a string, right? And just say, hey, string v.length, which is a size T. Because I'm doing pack type, it would engage these transforms, try to look for it and process it this way. So here I added 2 pack transforms for const char and string, and notice that I can. That's why I did this type decaying earlier in the code that adds those transforms. So I just say std string, but then my transform can actually accept const string reference, which is more efficient. Similarly, ignore this, do this cleanly comment. I now need a unpacking transform, right? So say here I pack one string and a second string, and then I want to say, okay, but the way I want you to unpack it is put them out actually in std string objects. It's better. I didn't want it to spit out const char star buffers because that means we'll have to allocate raw memory somewhere, copy this stuff there, and management of it would be a nightmare because you would have to remember to delete it. Otherwise, it's just packed and unpacked as a std string into a tuple. This tuple goes out of scope, it cleans itself. So let's see what happens there. So these 3 transforms, and also these pack size props, right? So again, when packing, we want to be able to determine how much size, how many bytes will this string take, right? So for a const char, instead of just doing a size of const char, which would be 8 bytes in this case, I just say, hey, no, the size would be pack size of whatever string length returns. So this is perhaps inefficient because it's actually running string length twice, but whatever. So it would say, hey, pack size, return value of string length. So in this case, size T, right? Plus an actual string length. So then we get an accurate measure of how many bytes any string we pass it would take, so that we can do this proper pre-allocation of the memory. So let's see if this works. And similarly for a string type, again, just pack size of what v.length would do plus an actual v.length, right? So it's obvious that the way I'm packing strings is just I pack the number of characters followed by the raw bytes. No null terminating character here because it's not needed because I already have a length. So then I pack it. Here we go. It's going to check the pack size for me, and let's see what it's going to get. and it's going to get the buffer size is 70 for those two strings to pack both those strings. So it's like, I don't know, 20 something characters here, 20 something characters here, plus 2 times size of size t. Okay, well, is this an accurate number? Let's see. We reserved 70 bytes, and after packing it, oh, look at that, buffer is actually 70 bytes. So all these pushbacks and copies into this buffer didn't cause us any memory reallocations. But again, this is purely optimization, and I could just as easily comment out those 2 lines, 227 and 228, and it would work just as well, and it would perhaps be simpler, but perhaps less efficient. I consider actually having a parameter to pack, something called like a hint. Maybe say, hey, this will likely take this many bytes, or at least this many, so maybe pre-allocate that many. But I found this this pack size proc to be a more elegant solution. Let's see, unpacking. So we unpack these 2 hard-coded strings back into tuple 3. We look at this. Here we are. The tuple contains now 2 std string objects with the actual values that we packed. Same thing here for packing of actual strings. So let's break here in this pack transform, and let's break in this unpack transform. So when I now go over this, here we are. This is the first string we got to pack. This is std string 1. Let's go to this again. Now this is std string 2. There we are. And then when we unpack here, don't mind the stack trace on the left. That's what happens when you're playing with lambdas and containers and so on and so forth. It's that's the code that gets generated, at least in debug mode. But here we are, because why? Because the framework tried to unpack, tried to find the transform. It found the transform for it, and then it's invoking this transform through this whole series of library calls. So if you're brave enough, go ahead, debug through it. I did once or twice. Not a pleasant thing to look at. So, all right, unpacking. So first we pull out a unpack type from the stream. And here, since I did a pack type, right, and pack type is a template, so whatever the type of this v length is, it's gonna pack that specific type. So when unpacking a type, right, you always have to tell it what type it is that you're unpacking. And there were 2 ways to do this. I could just do std string and then size type. That's just the type def defined inside a string, right? Or since I called v.length here, if you want to be certain, stop this. Another way to specify what type v.length would return would be to do something like decl type, which means you're going to be declaring a type, right? But in order to declare a type, you need a value of string. Now, decl type is executed at compile time, not runtime, but there's a way to declare a value, quote unquote, and then call a method on it, quote unquote, without actually doing anything at runtime. And the way to do this, you do std decl val. So you say, hey, declare me a value of std string. And then once you get this value, call that length on it. So this is, it's not as clean as saying, you know, std string size type, but it's another way to figure out what type that length was returning when we packed it here. So you can unpack it this way. This is nice because if this string was type def something else, and you change the type def instead of using string, you could use w string or boost string or whatever. You would only change one type def somewhere, and then assuming that that different type also had a length method, or it had that size type defined. The rest of the code, all it needs is just to be recompiled. It doesn't need to be changed one bit. Okay, let's change it back to what it was. And now I unpack the length. No, I didn't because I stopped the debugger. So let's see. So here we are, packing a string or unpacking a string. There we get the length. So we allocate a string. So here, like I told you, right, you get storage. So I'm sure you remember me talking about new operators and a placement new, and this is one place that it comes in very handy, right? Because the framework promises that I will give you a pointer to a memory location for std string where you can create this std string in. But it's not actually initialized. It's just raw storage. So now using placement new, I can say, okay, great. Now create me a string in this memory location that the framework gave me. Make it length something and give it a null characters to begin with, and then later on, once this string has the actual storage allocated for it internally, then I can just say, hey, unpack bytes from the buffer into the v.data, which is just a pointer to the underlying storage of the string, and this many bytes. So let's see what happens. And there, and it unpacked the string into this object. I said here, do this cleanly because string can take two iterators from beginning to end, but because this buffer input, it's an iterator that operates on std byte by default, string, or the rest of C++ for that matter, doesn't know how to convert from std byte to char. So that's why I had to do this this little hackery like that. But I'm sure I'll figure it out. Maybe I'll need to create some sort of an iterator adapter where it takes this input iterator and converts every underlying byte to a different byte representing type. Okay, let's see. Now let's step out of this until we get back into sane world. No, yeah, where were we? Let's stop these guys. We were transform. Okay, I think we are unpacking here. Let's just keep going. Let's go until we get there. Okay, there we are. So yeah, that's how you can add different types to the framework without that type, knowing anything about this framework, that it's being serialized and unserialized. Now the requirement on the type is that it is at least copy constructible when it's being unpacked, and I'll show you why that is. Because once I unpack this noisy type, you'll see the traces for what is happening to it. Okay, so here we are. Let's get rid of all these breakpoints again. Now let's go. And here I wanted to create this type n, right? This noisy guy, because it's not a standard type, right? It's not part of the framework. It's my own custom type, and I just wanted to show you that, hey, I can pack this guy, right? Without without this type needing to be aware of this framework. And here I didn't really add any packing transforms to this type n. It's just going to bit by bit copy it into the buffer, and this n just has an int, and there are two of them, so buffer 5, just 8 bytes. But I could very easily, if I wanted to, say, assuming this type had something auto. Let's actually be a little wiser about it. Decal type auto? No, that's all. Auto get value const return mv, right? So oftentimes these types will have those things. And when you're serializing a type, right, you not necessarily, you usually wouldn't think of it as serializing like a resource owning type, like something like a socket, right, or a database connection or something. Those I suppose make less sense to serialize. This is more for a POD, plain old data types. So if I wanted to better serialize this type, we can go through this exercise real quick. So now that I added this get value to this guy, let's see, it's an int. Okay, so I can do, before serializing this type n, I can say, okay, add pack transform for type n. And what's going to happen here? We are going to give it a little lambda. This text completion thing is driving me insane in Xcode. And we know that it's going to take const and ref b, and it's going to get a buffer output t reference it. It's important that those are references to iterators because you're advancing it, right? So you want the next guy to have this iterator that it's getting to also be advanced to the next location where to insert data. There, lambda. So let's say for packing n, let's actually add another transform here. It's being a little sneaky. What we're going to do, because we want, like we had these network byte order stuff here for different types, but not for ints. So before we pack the n, let's add a transform here that says, okay, for an int, type int, when you get it, pack its value as there, H2 and L, so host to network long. This actually operates on unsigned, but it's okay. And then when you are unpacking it, when you're unpacking an int, there, unpack a value of int. Actually, you should probably unpack a value of what H2 and L returns, right? So let's get that specific type. So that would be decal type of H2 and L of whatever. Let's give it a 0. Doesn't matter. This is only evaluated at compile time. So what I told it here is, hey, when you get an int, convert it to network long, pack it, and then when you're receiving an int, see how it was packed, right? So whatever H2NL returned, whatever the type it returned, unpack that same type, and then pass it through N to HL. So network to host long, and packing host to network long. So this way, those ints will also be serialized in a way that's machine independent. And finally, we don't need a size transform, I don't think, but let's put one anyway. So for an int, where are we here? So we know that when we were serializing an integer, how much space is going to take. This isn't really necessary because int here maps to the same number of bits, but it may not. So let's just take whatever H2NL would return and just return the size of that. So if it so happened that int was a 64-bit type and yet we packed it to a long, which would be a 32-bit type, then when we're pre-allocating memory for this buffer, we're gonna do it correctly. So that's that. And then finally, another set of pack transform for the actual n, not just its members. So then add pack transform for type n, and we would get const n ref here that would be passed to us. And when we would pack it, we would then say not pack value, but pack type and pack v.get value, whatever that gives us. So we just told the framework that, hey, for every type n that you get to serialize, just get its value, whatever the value is, and then say just pack that. And for the unpacking stage, we would just do more or less the opposite. So we would do add unpack transform for type n, and the proc, the purple here, would be, let's see, what is the signature of an unpack transform? It is a buffer input type, buffer input t, again, reference, right? So those iterators get advanced, and that advancement propagates to other next callers. And we know we would get a pointer to a storage where we can unpack this type n. And so what we would do here, first notice that type n has a constructor that can accept this value. So this is what we packed. We packed just this get value. So we can just do new in the space for n. Create a new n and give it, in this case, not pack type, but unpack type int, because that's what we right, that's what we were saving. Type int from the buffer, and that's it. Let's see if this works. Let's see if we can now break into all these places. 1, 2, and these are our. Let's put breakpoints in the spots where we're serializing the ints and returning their sizes. And let's see if the framework actually registers this and breaks in all these places. See my serializing an int somewhere else, so I don't trip up the debugger. Okay, so let's run it, see what happens. Building. I noticed it struggles building this code a lot. Here we are. Okay, so we have type n, and now we're going to pack two values of n, one and then another. So that's the problem. Let's see what happens. Okay, here we are. Pack transform is engaged for type n, and this is going to pack a type again the value. Let's keep going. There, we've picked up that we're packing an int. The value of this int here is 11, which is what this first n had. Pack another n, again get its value. This one has a value 17, like we expect. Again, look at this insane stack trace. That's the framework calling itself recursively through all these lambdas. Let's keep going. Here we are. So we packed it. Buffer 5, 8 bytes again. Let's look at the network ordering now. The first one was value 11, which is B, so it's the lowest byte, but it's actually packed in the highest location, right? So now we are in big endian instead of little endian. And same with the value 17. We unpack it. There. Now we're engaging the unpacking. So unpack transform for n from a buffer and create a new n in this storage we were given by unpacking just an int. Let's go. Here it's picking up this int using the unpack transform. So again, this is because I did unpack type. If I did unpack value, it wouldn't engage these transforms. By doing unpack type, you can define you know how to serialize simple types and then build on top of it. And I will show you this as the last example for serializing vectors of things. Then unpacking actual n. Again, unpacking another int. Here we are. So it created more objects here with 11, 17, did some copy constructs like it was supposed to. And now in tuple 5, we get back 2 instances of n. One with 17. This one I guess I'm showing as hex. New value as a hold. No. Value as hex. What is the number? Decimal. Here we are. So 11 and 17, exactly what we packed, right? These breakpoints. Here, just a bigger pack statement. Packs various different sizes, some characters, ints, hard-coded strings, string objects, ends. There, unpacking it back into tuple 6. All these values, are here. Simply value as character. This is yeah, so C++, pack 11, 14, 17, 2 strings, 2 instances of n. Okay, and finally, before we finally get to our protocol buffers after this hour-long introduction to my spectacular serializing framework. We can now build on top of it, right? Because we already defined how to pack a string, how to pack size t. So now we can say, okay, let's define strings as a vector of string. And we already know how to pack a string. We don't know how to pack a vector yet. So let's add this transform. So for every strings t, which is a vector of strings you get, you just say first, hey, pack type, size. In this case, it's just going to be a straight through. But if we remember, if we kept this this packing and unpacking of size t, then it would engage these transforms. So you could optimize it, right? You could say, hey, I know I'm going to be dealing with strings, but they're usually going to be short. So I can be quite certain that no string will ever be longer than 255 characters. So let's optimize it, save space this way by engaging these other transforms. So we're adding a way to pack packing vector of strings. Let's break here. And then we're adding a way to unpack a vector. So let's see what's going to happen. We now define a vec1. This is just a vector of 3 strings. Here we are, string 1, 2, 3. And now when we pack this guy here, we break into this pack transform for strings, pack type, it, size, bam. Here we just packed the size t, and here when we do pack type, let me show you that it's actually going to engage this code. So here we defined the way to pack a string. So when I actually try to do that, there we are. We're breaking now into this transform and packing a string, just packs its length and then its bytes. 1, 2, 3. Here we are. So we packed those 3 strings to the buffer. Let's see what's in this buffer. 56 bytes. There. It just packed the count of elements first. And notice here it packed it in little endian, right? Because I removed these size t transforms, and even when I had them, I wasn't doing any endianness switching. So here it packed it in little endian. So there are 3 for the number of elements in the vector. Then another size t here, 8 bytes, not efficient, but hey, it's there. 8, that's the length of the string, right? Which is string, that's 6, space 1, so that's 8. So there we get the 8 characters. Then another string of 8 characters, and finally a string of 8 characters. And then when we go and unpack it, we're going to engage the unpacking transform for unpacking of strings. So first we know it's going to pull out a size. And again, the type is going to be size type, because that's what b that size returns. So we're just telling it, hey, unpack the same type. Again, we could use this decal type like that. Either way is fine. Allocate this vector, reserve. There, unpack 3 strings into it. And finally, here we are. Buffer 7, and then output tuple 7. 1 tuple containing 1 vector containing 3 strings.